Hi, welcome to our third example for 3.4 properties of exponential functions. In this example, we're going to look at a half-life application question. So what we want to do is we want to take this information that we're given, interpret it, and then use it to generate an equation. So we're told that a radioactive sample has a half-life of 3 days. The initial sample is 200 milligrams. Okay, this half-life of 3 days means after 3 days, the 200 turns into 100, but it's not until 3 days happen. And then another 3 days after that, we'll just have 50, and every 3 days, it'll keep cutting in half. That's how half-life questions work. All right, so part A, it says write a function to relate the amount remaining in milligrams to the time and days. Okay, so let's actually do a quick graph here. I know it's not asking us to graph, but this will give us an idea of what is happening. So we're going to have our amount up here, which is in milligrams, and then we'll have time here, which is going to be in days. So we are starting with a sample of 200. So up at 200. Okay. Now it's not till 3 days, 1, 2, 3, that we have our first half-life, and we'll cut that in half and we'll be at 100. Then another 3 days later, so 4, 5, 6, that will cut in half, and our 100 will go to 50. And then another 3 days later, on the 9th day, we'll have half of that at 25. You guys get the idea. This is the exponential decay that is happening. So now we want to write an equation for this. So if you notice, this is the scenario when A is positive and B is between 0 and 1. Okay, that's basically the scenario that we have for the graph, showing a positive decreasing graph. So my function, I'm going to write it like this. I'm going to write it as A of t, and it's going to be equal to my initial amount, okay, times the factor by which this is changing. So this is half-life, so we want to keep multiplying by a half every compounding period. So my exponent is supposed to represent the compounding period. So be really careful that you don't just put t in here, okay? Because what happens is if you do this, when you go to put in 1 for the first day, this is going to cut in half, and you would actually have at 1 on the graph, you would be at 100. That's too soon. It's supposed to have a half-life of 3 days. So what we want to do is we want to modify this, and we want to write it over 3. That way, it's not until we put in 3 for t that we'll get 3 over 3, and that crosses out to just 1, and our exponent's now 1, and that would be the first compounding period. So when I write this out, I'm actually, I can write it from looking at the graph and my understanding of exponential functions, but I can also see how this really resembles the general form ab to the x. Remember, a is the y-intercept, which is what we have here. This is like my a value. And then this is the constant ratio that the function kind of follows. So this is like the factor that we multiply to get the next term. This is my value for b. Okay. The only thing that's a little bit unique here is the exponent. It's not just x. It's got to be modified to fit the scenario, which is a half-life of 3 days. So hopefully you can see how this relates to this. Now, to take this a little bit further, you can also remember this general formula. So all half-life questions follow this general formula where we have A of t equals A naught, that's a A0. It just means the initial amount. So in physics and in the sciences, whenever you see a symbol with a circle underneath, it means naught, and it always means the initial amount. So you could have initial time, or you could have maybe the initial force of something. So that's what this refers to here. So we'll just label this, and you can keep this handy in your notes. This always refers to the amount remaining, and in our case, the amount remaining is in milligrams. Okay, A naught is the initial amount, which is always the y-intercept, right? On the graph, initial amount, this is also in milligrams. So this is always going to be a half for half-life. You can always remember this is the factor by which each term changes. So it's like our common ratio, and for half-life questions, it makes sense that it's a half. T is time in days, and H is the half-life period, how long it takes for one half-life. Okay. These should always be like in the same frequency. So if your time is in days, your half-life period should be in days as well. Okay, if they give you a half-life period that's like 3 years, well, you don't want to put time in days, you want to put it in years. So make sure these match. Okay, so yeah, that is our function. So in blue, I'm just going to highlight it. So once you do a few of these and you kind of remember this pattern, they're really easy to do. And usually what the questions ask you is they'll say, predict how much is going to be left after 5 days. And you can just plug your time in and then you can find the amount. Okay, let's look at part B. So restrict the domain of the function so that the mathematical model fits the situation it's describing. So restrict the domain. Well, for a half-life question, there's no sense in going back in time. We're kind of looking at just time greater than 0. And we can see this is just going to keep decaying. Okay, we don't need to put a limit on the time. We can just say greater than 0. Greater than and equal to. So the domain, t is an element of the reals. T is greater than and equal to 0. Okay, just because we don't want to go back in time for the function. One other thing I do want to point out too, in real life, whatever this radioactive sample is, after many years, it's going to eventually not be radioactive anymore. That doesn't mean that this graph is going to cross the horizontal asymptote. It doesn't. So mathematically, this is going to keep approaching the t-axis, but never actually reach. But it's going to get so close, and eventually, in real life, this radioactive material, it will decay to 0. So the mathematical model works. Just because there's a horizontal asymptote doesn't mean that there's always going to be an amount of it that's still radioactive. That's not exactly true. So after many years, eventually it won't be radioactive anymore. Okay, that's it for our last example. Actually, that's it for this lesson. I'm going to be posting this in Teams, and you'll go ahead and answer these. Probably after doing this video, you might want to take a look at this and give it a shot, and then upload your solutions. Hopefully you guys found this helpful. I will see you later.